T-test for a mean. Let's go ahead and dive right into our student notes. More often than not, the standard deviation of a population is unknown, so the z-test is not typically used for testing hypotheses involving means. The t-test is used instead. The distribution of the variable should be approximately normal. Here are some properties of t-distribution similar to the standard normal distribution. Much like the standard normal distribution, the t-distribution is bell-shaped. Also, the t-distribution is symmetric about the mean. Third, the mean, median, and mode are equal to 0 and are located at the center of the distribution. Fourth, the curve approaches but never touches the x-axis. Definition: the t-test. The t-test is a statistical test for the mean of a population and is used when the population is normally or approximately normally distributed and the population standard deviation, sigma, is unknown. Here is the formula for the t-test. Notice that it's similar to the formula for the z-score, but not quite, with the denominator being slightly different. Once again, degrees of freedom are n-1. Using table F to find critical values for the t-test. Remember, for degrees of freedom larger than 30, round down to the nearest table value for the conservative approach. As degrees of freedom get larger, the critical values for the t-test approach the z-values. Here are some assumptions for the t-test for a mean when sigma is unknown. First, the sample is a random sample. And second, either n is greater than or equal to 30, or the population is normally distributed when n is less than 30. Again, these are assumptions that you can make for the t-test for a mean when sigma is unknown. Here's the procedure for the t-test by the traditional method. First, state the null and alternative hypotheses, then identify the claim. Second, find the critical values using table F. Third, compute the test statistic. Fourth, make a decision, reject or do not reject the null hypothesis. Fifth, summarize the results. Here is table F. You can find this in your book or in your online homework. Here's the procedure for the t-test by using the p-value method. First, once again, state the null and alternative hypotheses, then identify the claim. Second, compute the test statistic. Third, find the p-value. Fourth, then make a decision to reject or not to reject the null hypothesis. And fifth, summarize the results. Let's look at an example. Here, we're going to go ahead and find the p-value interval for each test value. Note here that the t-value and n are already given. So in table F, we choose the row for degrees of freedom equal to 14. Note here again, n is 15, therefore degrees of freedom is n-1, which is 14. Notice also that 2.321 is between table values of 2.145 and 2.624. The one-tailed areas above these values are 0.025 and 0.01. Therefore, with the p-value method, we have a range from 0.01 to 0.025. The p-value obtained using a computer or calculator would be 0.0179. Here's another example. Here we have a negative t-value, and n is 24, and this time two-tailed. Here, obviously, my degrees of freedom will be 23. 24 minus 1 is 23. But also notice that 1.415 is between 1.319 and 1.714. The table only shows positive values, but we can consider that negative 1.415 is between negative 1.319 and negative 1.719 as well. For a two-tailed test, the p-value is between 0.20 and 0.10 according to the table. That is, 0.10 is less than the p-value is less than 0.20. Once again, you can calculate the p-value using a calculator at 0.1705. And third, here we have again a negative t-value. Here n is 17, and this time we have a left-tailed test. For this problem, once again, we take the degrees of freedom as 1 less than n, in this case 16. In row 16, we find the value of t equals to negative 1.862 is between negative 1.746 and negative 2.120. Thus, for a left-tailed test, 0.025 is less than the p-value, which is less than 0.05. The p-value obtained using a calculator would be here 0.0405. Let's take a look at one more example. The average 1-ounce chocolate chip cookie contains 110 calories. A random sample of 15 different brands of 1-ounce chocolate chip cookies resulted in the following calorie amounts. At the alpha equals 0.01 level, is there sufficient evidence that the average calorie content is greater than 110 calories? Note the values in the table below. Step 1. State the null hypothesis. In this case, the null hypothesis is that the mean calories in a 1-ounce chocolate chip cookie is 110. Therefore, our H sub 0 is mu equals 110. However, the alternative hypothesis is that the mean calories in a 1-ounce chocolate chip cookie is greater than 110. Therefore, our H sub 1 will be mu greater than 110. This is our claim. In order to calculate the test statistic, we must find the sample mean and standard deviation for the sample. Utilizing methods from previous lessons, the sample mean here would be equal to 137.333, and again, using methods from previous lessons, the sample standard deviation is 24.11777. Step 2. We can now go ahead and calculate the test statistic, and plugging in our values into the formula that was from a previous slide, we get 4.389. Also, we can calculate the critical value. Here we get 2.624. And we're looking at table F with degrees of freedom 14, because we have 15 data values minus 1 is 14. And we're looking at the fact that we have an alpha level of 0.01. That's how I got 2.624. I invite you to pause the video here and verify that you agree that this is indeed our critical value. Here, the test statistic is more extreme than the critical value. So the decision will be to reject the null hypothesis. Or another way to look at it, our degrees of freedom 14, the test statistic is larger than 2.624. So the p-value will be less than 0.005, which also indicates that the null hypothesis is rejected at the 0.01 level. Again, the p-value can be calculated from a calculator at Our summary is that there is sufficient evidence to support the claim that the mean calories in a 1-ounce chocolate chip cookie is greater than 110.